If you've been here before, you know that I love tubes. This UE1 homebrew vacuum tube computer that I spent about 3 years building up uses around 350 tubes, I think. And this 1956 Bendix G15 uses about 460 vacuum tubes, and both of these machines fully work. I love tubes, but there is something seriously missing in this room, and that is something with Nixie tubes. But what even is a Nixie tube? I've got one right here, and looking closer, it looks just kind of like a short, stumpy little vacuum tube. What sets it apart from this 6AU6 that we have right here? Well, the differences are myriad, but the biggest one is that a Nixie tube is a display tube that looks absolutely baller. A little while back, I hooked up with a friend of mine, Eric, and we went to Japan. It was actually our second trip to Japan, and I used to live there for years and years and years, so it was kind of like going home for me. But we're both massive gearheads, huge car guys, so we rented a car and went on an absolutely epic road trip all around the country. But we're also massive fans of thrifting, so naturally I had to stop at every hard off that we came across and look for interesting or neat old stuff. And one of the hard offs that we went to had this little guy right here. This is a Casio ASA calculator, and it is full of Nixie tubes. However, it doesn't work. So today, we're gonna try and get this thing going. First things first, what's the difference between a vacuum tube and a Nixie tube? And well, there's many different ways to construct a vacuum tube, but in a vacuum tube like this little 6AU6 here, you have a cathode which is being heated by a filament. Now this cathode gets very, very hot, and if you put a negative potential on this cathode, the electrons are gonna boil off of that cathode. Now the electrons are looking for some place to go, so if you slip an anode or a plate into the enclosure and give it a positive charge, those electrons go screaming towards the plate. Now we can slip a grid right in the middle, and we can give this grid a negative charge or a positive charge to control whether those electrons can flow from the cathode to the anode. And in this way, we can use a relatively small voltage to control a massive amount of electrons moving between the two, creating an amplifier. So something like this little 6AU6 can take a voltage of, say, negative 10 volts to 0 volts and amplify that to, say, something like 50 volts to 150 volts. Massive amounts of amplification out of this. Makes them great for amplifying weak signals or signal restoration, or even using them in switching circuits in something like a computer. However, a Nixie tube does none of that. This is what's called a cold cathode tube. There is no filament in here. Instead, there is a very trace amount of a noble gas placed inside. I believe that most Nixies are going to be using a neon gas in there. Inside of this tube, we have 11 different electrodes. One acts as a common for the remaining 10, and those remaining 10 are cut into unique shapes. If we put a high enough voltage potential between the common electrode and one of those remaining 10 electrodes, that electrode will start to conduct, which means that the neon will break down and that electrode will glow. And when it glows, you can see the outline of the shape that it's cut into. And it just so happens that those 10 electrodes are cut into the shape of numbers. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So you can use this to indicate a value, which is exactly what this Casio ASA calculator is doing. It has a ton of Nixie tubes behind this little panel right here, and this is creating the numerical display to show the value that you just punched in on the magnetic reed switch keypad, or the result of the operation that you just performed. I think this thing is absolutely gorgeous. I love the faux wood grain on it, and I don't know exactly what year this one was made. I want to say 1969, but I don't know for sure. I do know for sure, though, that this thing is broken. It does not work right at all. We do get some signs of life out of it, but it seems very hit or miss, and something is definitely strange here. There is a whole lot of very rare ICs on the inside of this thing, and if one of those is dead, we could be in a very tough spot. But the only way to find out is to kind of first wrap our head around exactly how it's failing, then crack this thing open, take a look at the inside, and see if we can maybe pull the scope out and figure out what has failed. And then maybe we can order some parts, or maybe we put it back together and it stays. It's just a very pretty mantelpiece. Before we flip this power switch here, there is one thing that we do need to do, and that is that this calculator was built for use in Japan, and Japan uses 100 volts for their outlet voltage instead of 110 or 120. We need to actually understand exactly how the power supply is constructed, because that extra 20 volts could very well damage some stuff inside of this. So for the time being, I've got this plugged into a 120 volt to 100 volt step down converter. So this is going to be seeing the exact voltage that it would see in Japan. And then once we get it apart, we'll take a look at the power supply and maybe we can get it to work on 120. So let's go ahead and flip the power switch on here, and this is what it does. I mean, the Nixies lit up, which is awesome. They should be displaying 0, and it looks like they're displaying a whole lot of stuff. They're changing. That's not right. If I press a key, things happen, but not the things that should be happening. There it goes. It all died out. It does that as well. There are just 4 screws on the bottom in the corners, and once you get all 4 of those out, the entire thing cracks open, and it's just, it's stunning. It's absolutely stunning inside. Look at all of these gorgeous Nixie tubes right along here. That's just something that you don't see anymore, and I absolutely love it. Also, the magnetic reed switch keypad over here is absolutely fascinating. There are these tiny glass tubes, and inside of these tubes are 2 pieces of metal contacts. One of them has a slight bend to it that's keeping it away from the other one. However, when you push a button, it brings a magnet up beside the glass tube. This magnet pulls on the contact that is bent slightly away, pulling it into the other contact, making connection between the two and essentially pushing a switch. When you release it, the spring properties of the metal break the contacts and break the connection. And you can actually hear the click when you push this thing. But the first thing that we need to look at is the power supply. And unfortunately, I think it's kind of buried deep back in here somewhere. I mean, I can see the power transformer right here, but I can't really see anything else regarding the power supply. So I think quite a lot of this is gonna have to come apart in order to just give us access to that supply. Serviceability on this thing is surprisingly good for a desktop calculator. To get the primary PCBs out, it's just a single screw. But I'm a big dumb dummy and forgot that there are big wiring harnesses still attached to the main board. This large one here is the connection for the reed switch keypad on the front. A quick little pry with the screwdriver and off it comes. Then this little one back here is the connection for the power supply. It's a little tight to get to, but otherwise pretty easy to remove. And now we can pull the whole assembly out to get to work on it. I also finally found a date code on this thing. Looks like it was built in Showa 45, specifically on May 8th. In Japan, they like to indicate the year by specifying what year of the current emperor's reign it is. Emperor Hirohito reigned from 1926 to 1989, and this period was called the Showa era. The 45th year of Hirohito's reign would be 1970. At any rate, we're here for the power supply, which is this surprisingly simple PCB stuffed down here on the bottom. There are 3 screws holding it in place, and 4 more screws holding the power transformer in place. With those removed, we can get the full power supply free to work on. Well, here's the entire power supply. It's surprisingly simple. There is a set of schematics on the internet for a Casio 121B, which is supposed to be pretty similar, but that power supply didn't seem to match up with what I was seeing here. So I just reverse engineered this one and got this schematic here. And you can see it is dead simple. This power supply only produces 3 voltages. We have plus 180 volts, plus 90 volts, and minus 24 volts. So we need to confirm that all 4 of these voltages are looking good. The capacitors on here are a little gross looking, but I don't think that's because the capacitors are leaking, but that doesn't mean that they're good. They could very well be bad. Now I gotta be very careful here because there's 180 volts and 90 volts as well as some AC on here, and I could absolutely hurt myself. Also, there's no load on any of this, so we might see the levels kind of float a little higher than what they normally are, but I'll go ahead and flip the power on here. That should be generating voltage. Let's check this one right here. Minus 30 volts. Again, it's unloaded, so that might be okay. There's 97 volts and 197. All of our voltages look a little high. We should be producing 100 volts AC though, so it's probably a little high because they're unloaded. All right, let's try loading up the negative 24 volt rail here. I've got 45 ohms on it. That should give me, I don't know, something like 12 watts or something like that. And the 2SD91 pass transistor here, which I think is the primary regulator transistor for the negative 24 volt rail, it can support a maximum of 0.8 amps, which is 28 ohms. So we're not maxing it out, but we're definitely stressing it out. So we won't run it for very long, but let's see if we get a clean minus 24 on the multimeter here. So I'll go ahead and flip the switch. And that's actually a little lower than I was expecting, minus 18 volts. I wonder if we're seeing a bunch of ripple. And I think I've got everything hooked up correctly, so let's flip the switch and see what the scope shows us. Yeah, we are definitely a little noisy there. Look at that, that's like almost 5 volts of ripple. That's pretty wild. Let's center this trace up here. So I'm just gonna push this button here to center it. And we're gonna AC couple this thing. So I'm gonna come over here and hit this button and select AC. We'll close out of that. What this is gonna do is it's gonna capacitively couple the level that we're seeing, which should keep everything right here in the center. This allows me to get a much higher resolution on the amount of ripple that we're seeing. So we should see our ripple as a sine wave right in the center. Let's flip the power switch on here. And you notice that the trace went off the bottom because I was adjusting channel 2 here. So I gotta go to channel 1 and do DC to AC coupling. Helps if you know how to use your equipment. Let's flip the power switch on again. And yeah, there we go. Let's try to get our trigger adjusted. Right there. Look at that ripple. Let's take a single shot of that. And yeah, that's pretty gnarly ripple. Fortunately, there's no silkscreen or conformal coating on this board, so solder wick makes really quick work of desoldering the capacitor. Then it's super easy to just give it a pull and remove it. Let's plug it into my LCR meter here and give it a test. This is supposed to be a 220 microfarad capacitor, and the LCR meter is showing 360 microfarad. Even if I cycle through different frequencies, it seems to always be showing about 100 microfarad more than it should be. That probably means the capacitor is bad, but I couldn't explain the science behind why. Now, I don't have a spare 50 volt 220 microfarad cap, but I do have 3 50 volt 100 microfarad caps. I'll just tie them in parallel and we'll have a bit more smoothing capacity. Usually I'm not a big fan of blanket recapping, but I decided to pull and test all the capacitors and they were all not good. So they got replaced. Again, I didn't have the appropriate axial stuff at hand, so I had to get clever, but this should work perfectly. Got it all back together. Now, I don't necessarily think that this capacitor being bad was our sole problem, or any of the capacitors was our sole problem. I'm not that lucky, but let's at least see if behavior changed any at all. So we'll go ahead and flip the power switch on here. Nothing. Nada, zip, zero, zilch. Oh, whoa. Okay, I pushed a button. We got some zeros. It looks like our floating point is all over the place. Well, as soon as I moved the camera, the rest of the digits came alive. So it looks like all of our driver ICs are working at least. As I press keys, we can see that something kind of tries to change. But yeah, we're still like super duper unhealthy here. Something is very much so
Not right, but at least we're displaying something. That's awesome.
All right, that's good news. It means that we have good clean power going into the rest of the calculator now. And I actually went back with the scope to double check the negative 24 volt rail at the actual IC. And it's sitting at just a touch above or below. I don't know which way you say it when it's negative voltage. It's at like negative 24.5 volts. And there's like 0 ripples. So that's good. We've fixed the power supply. It is supplying good, clean power to the rest of the system. But as you saw, it's still clearly very broken. The good news though is that it's just a computer. A calculator is just a computer. It's a highly specialized, minimalist version of a computer, but a lot of the same techniques that we would use for troubleshooting a computer that has an unknown fault, we can use right here. And when you're doing that, you start with the basics, which is good clean power and finding a clock. And then after that, you go into divide and conquer mode. And we have good clean power, so let's see if we can find that clock. Now, the 121B calculator schematic that we're using for reference is excellent and an absolute lifesaver here, but the 121B and the 121A, and the 121A is the Casio ASA here, are actually quite a bit different. I mean, there's a lot of similarities there, and we can use this as reference, but there's still a lot of stuff that we have to figure out. For example, in the 121B schematic, we can see that the master clock is built out of a relaxation oscillator using 2 cross-coupled transistors. And I can actually find both of those transistors labeled PG right here on the board. That's our clock right there. However, in the 121B schematic, the outputs from that relaxation oscillator go through 2 different transistors to square off the signal, and I can't find those anywhere on here. So the clock is being generated in the same way, but it's being squared off and sent out to the rest of the system in a completely different way. However, because it's being generated in the same way, we can double check what that clock looks like by just clipping a little probe here onto the emitter of one of these transistors, just like that. Looking at the timing diagrams for the 121B calculator, it looks like the master clock should be at 50 kilohertz. Now, it's entirely possible that the 121A or ASA uses a different master clock frequency, but I think we should expect something kind of in that ballpark. So let's go ahead and flip the power switch on. Let's see if the scope picks up a clock. Yes, it does. My trigger's all in the wrong place. There we go. Looks like we're triggering cleanly. Zoom right on in. Now the clock has this slightly strange shape here because we're checking it directly on the relaxation oscillator before it's gone to any of the stages that would square it off. So I was kind of expecting that. Let's see if we can get a measurement of the frequency here. Yeah, there we go, 41.69 kilohertz. So it does seem like it runs a little bit slower than the 50 kilohertz that the timing diagrams for the 121B say, but this is the master clock, so everything should be synchronized to this. All right, the clock looks good, but we are seeing display errors. Sometimes half of the Nixies light up, sometimes all of them light up, and they're all flickering and going insane. Well, I think it's time to confirm, do we have a display problem or do we have a logic problem with the calculator? And there are exactly 12 Nixie tubes, and there are 12 transistors right here. These are the driver transistors for the anodes of the Nixie tubes. But we don't really have that many wires going to it. We have these brown wires that go to the anodes, and then we have this kind of bundle of wires that goes to this NEC chip right here, and there's only like 10 of these wires. So what we have going on here is a multiplexed display. We effectively are only displaying one single tube at a time, but persistence of vision makes it look like they're all illuminated at the same time. This way we can use the same 10 wires to select all of the elements on all 12 tubes here. And I went through and actually kind of traced out a little bit of what's going on here to try and figure out what I could clip onto. And these are moving like a full 180 volts. But I think if we clip a probe lead right onto this resistor right here, that is a 12K pull-up to 180 volts for the base of this driver transistor right here, which is going to be driving the anode of this tube right here. So we should see the control signal going into the base of this transistor at a regular interval. We're looking at either 0D0 or 0D12, and you can see it goes on for one full digit, which is going to be like a handful of clock pulses, and then it's off for the rest of the digits. So I've got the base of that transistor hooked up on channel 2 here, and I'm expecting this to go all the way up to 180 volts. So I'm actually going to AC couple this one here, and I'm using my probes in 10x mode, so we shouldn't fry anything. With AC coupled, I have no idea what the amplitude of the signal is going to be. I've got it set to 10 volts per division right now. Let's see what happens. Let's kick the power on. Yeah, we can see some action on there. As these things flicker, we can see that this thing gets unstable. All right, let's see if we can get a scope shot of this. I'll hit single here, and that's not at all what I thought it should look like. What? What is going on here? Let's make it a little bigger so we can kind of see what's going on. Let me hit run again. Single. That doesn't look at all like the schematic says it should look. And here's where we run into a bit of a problem. You can see it's on and displaying garbage. The buttons don't do anything, but our digit timing actually looks good. This green trace that's being displayed here is kind of what I was expecting to see for digit timing. However, we saw earlier that it didn't look good. It looked like complete and utter total chaos, and every so often the display's just like totally cut out, and our digit timing also dies at that point, which just like doesn't make sense and feels very, very wrong. And if we look at the schematic, this kind of confirms our fears here. So this is, again, the 121B schematic. We can see that the master clock is generating two clock signals, what they call OC and OT. And then if we look just below this, we get to a section called digit timing, and we can see that the OT clock is being fed into 13 D flip-flops. Now I can see these D flip-flops on the actual ASA PCB here. There are 3 metal can ICs underneath the Nixies, and these are the D flip-flops. And each one of these flops is set up with the Q output being fed into the D input of the next flop. This creates a nice little ring counter. Essentially, you have a pulse that just propagates all the way around. And if you take the last stage and connect it up to the first stage, you create kind of like a never-ending train of this pulse moving in a circle, which is exactly what we want. It's brilliant. I love this kind of engineering. But we're seeing that it's misbehaving, and if the clock input into it is coming directly from the master clock, which we see is pretty much stable all the time, that implies that maybe the clock input and the master clock output are not as shown here on the 121B. Same with the initialization logic. So it's time to do a bit of reverse engineering. Ultimately, I'm gonna have to just shut the whole thing down, get the Nixie tubes out of the way, get scans of both of the PCBs here, and start doing a bit of reverse engineering to connect up bits that we know are correct and match the 121B, and change the bits that we know don't match the 121B, kind of creating a new hybrid schematic that's much closer to the 121A or the ASA that we have here. But this is gonna take some time. Reverse engineering is not a quick process. So this is something that I'm gonna have to dig into at night over the next couple of weeks, but I am absolutely in love with this calculator. I think it's really fascinating, and I am really excited to dive into the logic of how this thing is doing computing. Like, how's it doing addition and subtraction? How's it moving data in and out of memory? How's it displaying that data onto the Nixie displays over here? This is like a really refreshing and enjoyable kind of journey into minimalist computing. I just am absolutely smitten with this thing. So I hope you guys are as excited about the upcoming episodes on this as I am. And really, I want to thank you guys so much for watching, and I hope to see you in the next one.